Okay, our A inverse matrix, again, is the matrix we have here on the right, where the identity matrix is on the left. The steps we've taken to do this, you really don't want to get too hung up in the arithmetic of the fractions. That's just simple arithmetic that we teach in 5th and 6th grade. You haven't done it probably in 7 years since I put a calculator in your hands and encouraged you to forget everything you know about math, about basic arithmetic. But the basic arithmetic is not difficult. If you do 2 or 3 of these, you'll catch on. It'll be clear to you. It's not really all that mysterious. In any case, we do the arithmetic. And also, I'll mention again, I don't seriously expect you to be able to do the arithmetic accurately and get everything to work out. It would take me a long time to do that. If I was going to do it reliably, I'd have to write it out very meticulously and check my steps at almost every step. Now, there are a couple of other things I could do to cheat. I can find the determinant of the coefficient matrix and make sure I'm getting denominators that kind of look like that determinant. And if you think back to Cramer's rule, you'll understand why, but that's not really necessary. Okay, so in any case, your A inverse matrix, and I got that written way up there, and the matrix written down here. Let's put it here where it looks a little better. Okay, the A inverse matrix, just copied down from here. You can check and see if I copied it correctly. I think I've got it. Just doing a quick double check. Yeah, I think I've got it. Okay, it'd be written like this. Now, looking at all those fractions, you can just about go blind. I'll tell you, you can factor out that 1/97th and just multiply that then by the matrix of the numerators. And the meaning of 1/97th times this should be pretty clear. It gives you this. And you can reconcile that if necessary, but it's a fairly obvious step. Okay, so here's our A inverse matrix. It's going to be more useful if we put it in this form. It's going to be easier. It's going to be easier to multiply by the positive numbers and everything. Okay? So what do we need to do? We need to do A inverse Y. So let's get the board over here where we can see the whole thing. And I believe this was clear before. You could see this. I'm pretty sure you could see this, but again, I just factored out the 1/97 and wrote down the numerators of all these fractions. Okay, well, then our x vector is A inverse times our y vector. And that's going to be A inverse. Now, I've actually forgotten what in the world our original y vector was. Hopefully I've got it written over here. No, I don't. I'm going to have to pause for a second and find those numbers. I think it was something like 7, -1, 1, or something like that. But let me find it. Okay, sorry for the kind of a dead space there. I clicked on the stop, but it didn't stop. Okay, so anyhow, the y vector is, as I said, 7, -1, 1. I believe that's correct. I better go back and take one more look. So it's not going to be very difficult to multiply this vector by this matrix. We're going to use this form, which means we'll be able to multiply this matrix by the vector and then divide the results by 97. So let's do that. That's going to be 1/97 times the matrix 11, -12, 18, 18, 22, 3, 19, 23, -13, multiplied by 7, -1, 1. What's that equal? Well, you're going to get the 1/97th, and then it's going to be times what? 11 times 7, first times first, second times second, minus 12 times -1, plus 18 times 1. Okay? The second is going to be 18 times 7, plus 22 times negative 1 plus 3 times 1. The third is going to be 19 times 7 plus 23 times negative 1 minus 13 times 1. Now, those are all straightforward numbers, and not much more than, and I wrote down 19 here, it's 97. So you're going to have 1 over 97 multiplied by what? Well, that's going to be 77. 12 times 1 is 12, and the two negatives make it positive. And then we're going to have 18. Okay, 18 times 7, 70 and 56 is 126. And 7 times 20 is 140. Subtract 2 times 7, 126. It works out. Minus 22 plus 3. And then 19 times 7, well, that's 20 times 7 minus 7. 140 minus 7, 133. Minus 23 minus 13. So what's that? That's 1 over 97 multiplied by 77 and 12 is 99, and 18 is 117. 126 minus 22 is 104, plus 3 is 107. 133 minus 23 is 110, minus 13 is 97. So that equals 117 over 97, 107 over 97, getting bunched up here, 97 over 97. Of course, 97 over 97 is 1. 97 being prime, these other two aren't going to reduce. But that's equal then to what? That's equal to our x vector. What's our x vector? X, Y, Z. Which means that our solution is x equals 117 over 97, y is 107 over 97, z is 97 over 97. Now let me double check that. And then we'll go on and verify the solution by plugging these numbers into the original equation. Okay, not too surprisingly, I had a couple of errors. First error that kind of needs to be corrected in a couple of places. This was 32, not 22, which makes this number 32, and this number 32, and this number 32, and this number 32. So just replacing the 22s with 32 there in the middle, I get this. And of course that makes this number 32, and that makes this number here, instead of 107, it's only 97. Now it's going to be very convenient because 1 over 97 times 97 is going to give us 1. So down here we're going to get 97 over 97. And the other error made a little bit later, in copying this down, I copied my minus 2 here as a 12. So I've changed that to a 2. That's going to change this to a 2, change this to 2, and the effect that's going to have is, by gosh, we're going to get 97 here. So now, instead of 117, we've got 97. And look at what happened. We've got 97 over 97, 97 over 97, 97 over 97. That's 1, 1, 1. Means x equals 1, y equals 1, z equals 1.